So if you think about it, John did a good job of talking about a lot of the applications and the performance requirements of 5G. And you'll hear more and more people say that 5G is going to change everything. It's going to change our lives. It's going to change all parts of the network. And that's a key point, all parts of the network. Because if you look in the news today, most of the 5G attention is around the radios. It's the upcoming handsets. You know, when will I get my brand new iPhone 12 or whatever they're going to call it? Very little attention is being spent on the wireline network. But if you actually think about it, what is a mobile network? I mean, it's a massive wireline network with radios and antennas hanging off the end of it. And your typical service path is from your user equipment, which is your smartphone, and you're pulling content or running an application off some data center somewhere. So it's that network in between the radios and the data centers that will ultimately dictate the performance of your end-to-end service. And we're going to talk a little bit about the overall network, but we're going to focus a lot on the front haul space. That's the battleground right now. The industry was kind of trapped in a closed and proprietary CPRI-based 4G architecture, at least for the CRAN application. And for the 5G space, the industry wants to get out of that, in particular the mobile network operators. They would like to have something far more open in the front haul space. That's between the radios and the baseband units, which I'll talk about. And I think the time is now. If the industry doesn't adopt an open approach, we may have another decade of proprietary and closed architectures. And that's why so much attention is being spent on it now. And that's from the mobile operators who actually deploy the equipment, right down to the chipset vendors who are building chips to enable open front haul networking. So if we look at the end-to-end network, when you connect a user, a mobile user, he's typically pulling content or running some application from a data center. And that could be man or machine, right? If it's a human watching Netflix, for example, my son keeps getting me to watch Narcos, you're pulling it off a data center somewhere. If it's a machine, he's probably also pulling data off a data center. So that's the end-to-end service path. So it's pretty much made up of two domains. You have the wireless network domain, and this is the radios, the antennas, it's the handsets. There's a lot of very key technologies here. This is where all the attention is being spent right now. How do we get the bits over the airwaves? And a lot of attention will be spent going forward there. And then we have the whole the wireline network domain. And that's from the radios all the way back to the data center. And there is some cases of the wireless backhaul as well, but we're focusing on the wireline side, which is, for the most part, copper's kind of disappeared from the 4G space. And 5G is all going to be about fiber wherever you can, and you'll have some wireless segments where you must. So if we look at the radio access network, we're not going to talk about today. We're going to talk about this part of the network, mainly on the front haul, mid-haul, backhaul side. Again, mid-haul is a new term that's come to market. It means different things to different people. But it basically is the connection between two network elements of which are newly discovered. And then we have the intra-data center connectivity. So you can see here there's a lot that has to change. If you want to guarantee the end-to-end performance for these 5G use cases, you have to make sure that every piece of that network, from the user equipment to the data center, and we're also including storage and compute as well, have to be up to speed to give you those performance guarantees. So when 5G has a lot of promise, it also has a lot of complexity. It's going to be a multi-year journey. It's not an upgrade. It's a multi-year journey on the wireless and the wireless sides of the house. So we're going to start at the point where all the problems started, the challenges and the opportunities, if you like, that we're facing today. So for those who are not familiar with how the radio stations or the cell sites were actually built out early on, it's something that's called distributed RAN, or distributed radio access network. So you would have those towers that everybody wants in their neighborhood, just not near your house because they're ugly. But you want these towers, and you would have the remote radio heads that are sitting at the top, and you typically have your baseband unit sitting at the base of the tower, controlling the radio functions. Early days, this was all done using copper, very expensive, very complex, susceptible to EMC and EMI, and it was very power hungry. So some smart guy came along, I think it was around 2003, and he said, well, why don't we put fiber from the top to the bottom? And we clear up a lot of those issues, and that's what happened. So the interface was the CPRI interface, a common public radio interface. It was done over optical connectivity, optical technology, and it allowed you to communicate between the radio heads and the baseband units at the base. The height of the tower is roughly 200 to 400 feet. Nobody really thought about latency back then, because the initial design of CPRI was to have that the tower sitting at the base. But then another smart guy came along and said, well, wait a minute, that's fiber. Fiber goes long distances. Why don't we take the baseband units, and instead of putting one at the base of every tower, we can centralize these in a protected central office, and then we can just run fiber out to the remote radio heads. So much easier installations out in the field. You can have all these baseband units in a protected environment, and you can also have the communications between the baseband units at different cell sites allow you to do a lot of really cool things, such as coordinated multi-point connectivity, intercell interference, and so on. The problem is the CPRI protocol was not designed to go over very long distances. You can get upwards of 20 kilometers between the baseband units and the remote radio heads, but you're still highly constricted with latency, roughly 200 to 250 microseconds. And if you think about it, when you start moving these things or putting a distance between them of multiple kilometers, you start to look at the propagation of light in Mother Nature, right? We have a delay, but there's also the network elements, the transport network elements. They may sit in between the radio heads and the baseband units. So, created a lot of problems from a latency perspective. And this is one of the reasons, besides, the lack of fiber out to all these websites, all these cell sites, 4G centralized RAN didn't really take off in great numbers. There's also another problem with CPRI. This is communication between the radio heads and the baseband units. And if you read through this, if you're looking at giving some end user 150 megabits per second of bandwidth, on the front haul side, it's generating almost 2.5 gigabits of traffic. So you can just do the math here. This is for one CPRI stream. So each CPRI stream is for each antenna. So if you're looking at massive MIMO, 64 by 64, you're looking at many, many more users, and you're looking at much more capacity per user. Once you add these things up, CPRI no longer makes sense. So something had to give. We had to come up with a new CPRI. They're calling it Enhanced CPRI, or eCPRI. You may have seen this acronym. And it's trying to solve some of these problems. But we still have to solve some of the other issues as well. Typically today on CPRI, you have one CPRI stream per wavelength, or even one per fiber, which also doesn't scale very well. Most of the larger MNOs, they want to put a network in between the radio heads, a multi-point network between the radio heads and the centralized baseband units. And that's what we're going to talk about today.